Okay, let me give you the first examples. Example 6.4 in the textbook. Okay, it's the problem is like this. There's a nozzle held by a flange. Okay, and the nozzle, you have inlet and outlet. Okay, let's say inlet is 1, outlet is 2, the 2 locations, right? Pressure at the inlet is 105 kPa absolute. Okay, the pressure at the outlet 2, P2, is 101.3 kPa absolute. You know, the atmospheric pressure is 101.3 kPa absolute. So you better convert the both pressure into gauge pressure for simplicity of your calculation. So P2 is atmospheric pressure, it's 0 Pascal gauge. So P1 will be 3.7 times 10 to the 3 Pascal gauge, 3003, 3000 and the 700 Pascal gauge, right? These two pressures given inlet and outlet. Pressure drops. Okay, diameter of the inlet is 60 millimeter. Diameter at the outlet is 10 millimeter, 6 times decrease of the diameter. Okay, so density is 1.22 kilogram per cubic meter, which is air. Okay, so the question asks, what is the force required to hold this this nozzle in place? You know, you have the speed difference, you have pressure difference. There will be a force, right? A resultant force from the momentum principles. So you need to hold it. You need to hold it. Otherwise, the nozzle gonna be pushed away, right? You have to hold it. So what is the force required to hold it? You put a flange there to hold it. So how strong the flange should be? Okay. So what is the force required to hold this nozzle in place? That's the question. Okay, so the problem solving process is like this, like I showed you before. Okay, you have to have 2 diagrams, free body diagram and the momentum diagrams for this problem. I think this is the first example. It's a simple example. It's 1D momentum problem. So the calculation will be a little bit simple, okay? Not too difficult. So for the free body diagram, okay, this is the free body diagram. You draw this country volume, you identify the country volume and sketch it, okay? So on this country volume, which is this portion of the nozzle, right? So you have, well, first of all, you have a force, F, the force required to hold it. Remember, I talk about it in chapter 3 when you draw free body diagram. If you detach any object from a support, which in this problem, you detach the nozzle from the flange, you have to replace by the force, reaction force, right? You have the force required to hold it. That's the force. If you detach it from the flange, you replace it by a force, okay? So the direction of the force doesn't matter. I don't know the direction. I just place that force into the positive x direction, okay? If it turns out to be negative, that means the force will be the other way, okay? So I don't know, then I put the positive x direction, okay? Then you have 2 pressure forces, P1A1 and the P2A2. I guess that's it for the force, right? For this problem, these are the forces. Free body diagram complete. Then the momentum diagram. Okay, momentum diagram, just draw the momentums for the particular problem. So for this problem, you have 2 momentums. You have only 1 inlet and 1 outlet. If you have multiple inlet and outlet, you will have multiple momentums, right? So in this problem, and this is the momentum. It's uniform velocity. It doesn't say the velocity at the inlet and the velocity outlet are non-uniform. So we assume it's uniform, okay? For the pipe flow, we can assume it's uniform. So uniform velocity, you have mass flow rate inlet, m dot I vi. Let's keep it this way, okay? We can calculate those velocity, but let's keep it this way. And the mass flow rate outlet is m dot o vo, or you can replace it by m dot 1 v1, m dot 2 v2, right? But I'm trying to be consistent with our general equations, so I'm still putting I and the O here, be more clear. Okay, So based on these two diagrams, the process is very easy. Okay, you write the equation sign first, equal sign first, equal. Okay, you know the left hand side of this equal sign will be your summation of force based on the free body diagram. Okay, the right hand side of the equal sign will be the change of momentum based on your momentum diagram. Okay, so for this problem, easy. Summation of force along x direction, 1D, right? Only x. It will be P1A1 minus P2A2 plus F. Be careful with the sign, okay? P2A2 is 0 because P2 is 0 gauge. And momentum differences is momentum out minus momentum in, okay? Mass flow rate out, O, VO minus mass flow rate in, I, VI, okay? So we can rearrange it because you know conservation of mass, the mass flow rate has to be the same for this problem, right? For this steady state problem. So momentum, mass flow rate in and mass flow rate out should be the same. Let's just use m dot to represent the mass flow rate. And the VO is V2, VI is V1. So it will become mass flow rate times parentheses V2 minus V1. So this is the equation based on the free body diagram and the momentum diagrams, right? Okay, so our goal is to solve for F. Our unknown is F, so it is in the equation, which is good. Our equation is correct. Okay, the selection of our equation is correct at least. Okay, your F is there, so our goal is to solve for F. Okay, so do we know everything else for solving F? Well, we know. Okay, we know P1 and A1, that's given, okay? P2, A2 already 0. And we know mass flow rate R equal to mass flow rate in equal to m dot. But we don't know the value, mass flow rate as well as V2 and V1. We know none of them in the right hand side. We only know P1 and A1 in the left hand side. So what is your goal next? Obviously, we don't know this, right? The goal is to find mass flow rate m dot as well as V1 and V2. Okay, so what equation we're going to use to find the velocities? You know, mass flow rate is based on the velocity. If you know velocity, you know the mass flow rate. So the principle, obviously, you know, at this moment will be you need to use chap6-2 Bernoulli equation, right? We use Bernoulli equation to find the velocities unknowns. So from 1 and 2, obviously, location 1, location 2, write down the Bernoulli equations. P1 gamma Z1 half rho V1 square equals P2 plus gamma Z2 plus half rho V2 square. Okay, we can get rid of gamma Z1 and the gamma Z2 because they are on the same elevation, okay? So it becomes P1, P2, V1, and V2. Okay, but still, P1, P2 are given. P2 is 0 actually, right? P2 is 0, but P1 is given. But still, we have two unknowns there, right? V1 and V2. So we need one more equations. What principle we use for the next equation? Must be conservation of mass because V1A1 equals V2A2. For this steady state, uniform velocity, conservation of mass equation will be V1A1. Volumetric flow rate are conserved. They are equal at the inlet and outlet. You can say mass flow rate equals, right? But rho, their density is the same. So rho V1A1 equal to rho V2A2. So rho can be cancelled. So you can just compare the volumetric flow rate. So A1 and A2 are given because diameter is given. 60 millimeter and 10 millimeter. So you have two equations for two unknowns. V1 and V2 are the two unknowns. Okay, so two equations. You should be able to solve for V1 and V2. So if you calculate it, V1 will be 2.16 meter per second and V2 is 77.6 meter per second. Notice there are 36 times difference. Okay, the diameter is 6 times difference. Right, 60 millimeter and 10 millimeter. Okay, so the area will be 36 times the difference, right? A1 is 36 times of A2. That's why your velocity is also 36 times. A1 is 2.16 and the V1, I'm sorry, V1 is 2.16 and V2 is 77.9 meter per second. So the mass flow rate, you can use either V1 or V2 to calculate the mass flow rate. Okay, 0.0074 kilogram per second. Then you can substitute everything, all the values into this equation, momentum equation, right? To calculate the force is negative 9.9 Newton. Okay, that's the force required to hold it. So why is negative? Negative 9.9 Newton means you need the force go the other way. It's opposite to the direction of the force we draw on the free body diagram. That makes sense. The flow is from left to right. Your force is from right to left to hold it in place, right? So that's why it's negative 9.9 Newton. That's the required force to hold this nozzle in place. Okay, this is our first example, 1D conservation of momentum problem.